Welcome back. Today we'll be talking about the side splitter theorem, a theorem in geometry that allows us to speak regarding similar triangles. So you might remember we talked about a mid-segment, and a mid-segment is a segment that specifically connects the midpoints of two sides of a triangle. And when we constructed this mid-segment, we produced a segment that is both parallel to the base and is exactly 1/2 the length of the base. We'd worked on this before, and today what we're going to be working on is an extension on that. In other words, the mid-segment concept is a subset of this now larger concept that we're learning about called side splitter. So what makes this extension work for us is that it's no longer something that has to happen right in the middle. In other words, as long as I can produce a segment that extends across the triangle and is parallel to the base, then it doesn't matter where that is. It doesn't have to be halfway. But by being parallel, we know that this angle and this angle are congruent, and this angle and this angle are congruent because they're corresponding angles across parallel lines. Therefore, we end up with two similar triangles by angle-angle similarity. As a result, we can say that the relationships among the sides constructed or produced by these split sides have a relationship. Now, because the triangles are similar, we can visualize that this is the bigger triangle, this is the littler triangle. In the little triangle, we've got A and C, and in the bigger triangle, we've got A plus B and C plus D. And because these triangles are similar by angle-angle similarity, we can say that the sides are proportional. Therefore, A is to A plus B as C is to C plus D. Now we can use that anytime we want to find the missing parts. In other words, I could say that this length is to this whole as this length is to its whole. There is an opportunity for us to create a theorem or a shortcut that allows us to do some things more quickly, more efficiently. So if we take this initial proportion, we can use the reciprocal property of proportions to say that A plus B over A is equal to C plus D over C. And then we can recognize that this is really a fraction of B plus A plus A plus A equals C over C plus D over C. And this is 1 and this is 1, so if I subtract 1 from both sides, I get B over A is equal to D over C. And then I can again apply the reciprocal property, and I get this relationship. In other words, this side is to this side as this side is to this side. And of course, with the exchange property, I could also say that A is to C as B is to D, to say that this is to this as this is to this. How might we use this? Well, let's say that we had a side split with an appropriate parallel line, and we knew that this was 6 and this was 8, and this was 9 and this is x. We'd first identify that this is a candidate for side splitter because our segment in the middle is in fact parallel. Then we could say that the relationship between these two, the proportion set up with that ratio, is equal to the proportion set up with the other two. In other words, 6 is to 8 as 9 is to x. Then I can simply cross multiply to solve. And I find the length of x. Now I could have done this by treating it as it was similar triangles. This was side splitter. In similar triangles, I would have had to say that the hypotenuse looking side of the little triangle is to the flat side of the little triangle as the hypotenuse of the bigger one is to the flat side of the bigger one. And this would work as well. I'd combine terms to say 6/9 is equal to 14 over x plus 9. I'd cross multiply and get 9 times 14 is equal to 6 times quantity x plus 9. 9 times 14 is 126 is equal to 6x plus 9. subtract 9, and I get 115. That work right? Let's see, 9 times 14, 26, yep. Subtract 9 and I get 117. That's what it is. Equals 6x. Divide by 6, divide by 6. And something didn't work. Oh, I forgot to multiply this by 6. So this should be 54. That's why it wasn't working. So 126 minus 54 is equal to 72. That's what I'm expecting. Divided by 6, divided by 6. 12 is equal to x. In other words, we get the same result whether we use the side-splitting theorem or the similar triangles theorem. Now, of note, and to be cautious about, is the fact that some scenarios that look like side-splitter don't actually apply the side-splitter theorem. In other words, what if I were to give you this picture and tell you that this side is 10 and this side is y? Well, I might be tempted to say 6 is to 8, right? This is to this, as 10 is to y. And think about it as a side splitter. That actually is not going to work. Why not? Well, let's do it by similar triangles. The small triangle has a side length of 6 relative to this side length of 10. In the bigger triangle, I can align my y and the 10 because they're corresponding angles, corresponding parts, which is sides. But what is my corresponding part to 6? 6 is this whole length. So in my big triangle, that side should be the whole length of 6 plus 8. And I should be able to solve that. So 6 times y is equal to 14 times 10. 6y is equal to 140. Y is equal to 140 divided by 6. So y is equal to, what's that going to be? I can say that 140 is 2 times 7 times 5 times 2. 14 times 10, and this is 2 times 3. It's not going to come out evenly, so it's going to be 70 thirds. But nonetheless, I can find the value not using side splitter. I can find it using the similar triangles concept. And that's the concept of side splitter theorem. Thank you.